In this video, we will demonstrate the calculations for the titration of a weak acid experiment. We will work through an example calculation for the titration of a weak acid experiment. Please be aware that the data we are using in this calculation are not the same as those that are from the actual experiment. We have two goals for this experiment. First, we want to calculate the molar mass of the unknown acid. Second, we want to determine the pKa of the unknown acid. Please keep in mind that in these example calculations, we will be using a different weak acid than from the experiment video. However, the same NaOH solution was used as the titrant as in the experiment video. For these calculations, the mass of the unknown acid that was titrated was 0.421 grams. The concentration of the sodium hydroxide was 0.0935 molar. The first step in our data analysis is to plot the titration data on the graph paper provided on Canvas. Please remember that your titration plot will look slightly different than the one in this video. The overall structure of the plot and the analysis will be very similar. First, we notice that there is a region of very steep increase, approximately at 25 milliliters of base added. This is the equivalence point region for our titration. The equivalence point is approximately the midpoint of this steep increase. Once we have identified the midpoint, we use a ruler and draw a line directly toward the x-axis. The value where the line crosses the x-axis is the equivalence point volume, or VEQ. In the case for this calculation, VEQ is equal to 23.8 milliliters. Now we can discuss the steps for calculating the molar mass of the unknown acid. First, we calculate the moles of sodium hydroxide required to reach the equivalence point. Second, we remember that there is a 1-to-1 stoichiometry for the neutralization reaction. This is due to the fact that we are titrating a monoprotic acid. From this stoichiometry, we can calculate the moles of acid that are present in our system. And finally, from the mass of the weak acid and the number of moles titrated, we can calculate the molar mass. The first step is to calculate the number of moles of sodium hydroxide that were required to reach the equivalence point. This is simply done by multiplying the equivalence point volume in liters by the concentration of the standardized sodium hydroxide. This gives 0.0238 liters times 0.0935 molar, or 2.23 times 10 to the negative 3 moles of sodium hydroxide. Next, we use the stoichiometric ratio of 1 mole of sodium hydroxide reacting with 1 mole of weak acid to find the moles of weak acid that were titrated. From this, the number of moles of acid is equal to the number of moles of sodium hydroxide times the ratio of 1 mole of acid to 1 mole of sodium hydroxide. Using our values, we find this to be equal to 2.23 times 10 to the negative 3 moles of sodium hydroxide times 1 mole of acid per 1 mole of sodium hydroxide. This gives 2.23 times 10 to the negative 3 moles of acid titrated. The last step is to divide the mass of the unknown acid by the number of moles to obtain the molar mass. Recall from earlier that the original mass of the unknown acid was 0.421 grams. The molar mass of the acid is equal to the mass of the acid titrated divided by the number of moles of acid titrated. This becomes 0.421 grams divided by 2.23 times 10 to the negative 3 moles, for a molar mass of 181 grams per mole. We are now ready to determine the value of pKa for our weak acid. We need to return to the titration plot to do this. Recall from the previous lecture that when we have a weak acid, HA, the Henderson-Hasselbalch equation takes the form pH equals pKa plus the natural log of the ratio of the concentration of A minus to the concentration of HA. When the titration volume is equal to 1/2 VEQ, then we have reacted off exactly 1/2 of the weak acid. As a result, the concentration of HA is equal to the concentration of A minus at this volume. Therefore, when V is equal to 1/2 VEQ, we know that the ratio of A minus to HA is equal to 1, and therefore pH is equal to pKa plus the natural log of 1. But since the natural log of 1 is equal to 0, at 1/2 VEQ, pH equals pKa. Let's return to the titration plot. Remember that VEQ was determined to be 23.8 milliliters. This tells us that 1/2 VEQ is equal to 11.9 milliliters. We then use a ruler and draw a line directly up from 11.9 milliliters on the x-axis until it touches the titration curve directly above it. Then we draw a line back to the y-axis. Where this intersects is a pH value of 3.88 in this particular example. This pH value should be equal to our pKa for our weak acid. Therefore, the estimate of the pKa for this unknown weak acid is 3.88. That concludes the calculations. You will perform these same calculations, but using the data provided with the video. Remember that the concentration of the sodium hydroxide used in the video is 0.935 molar, as in this example, but the titration data and the mass are different for the actual data provided. Additionally, you will be provided with a list of candidate acids. Based on your results, you will select the best candidate and perform percent error calculations. We have now concluded the discussion of calculations for the weak acid titration experiment. The data have already been posted on Canvas, and guidelines and data sheets will follow.